As you watch this water rise and fall, it's tempting to think about tides as something simple and passive. The ocean just coming in and going out, almost like it's breathing. That description fits what we see, but it doesn't explain why it happens. It doesn't tell us what forces are involved, where the energy comes from, or why tides behave so differently in different parts of the world. Today, we're going to take this very familiar phenomenon and rebuild it from the ground up. We'll start with what causes tides in the first place, then work outward to understand why tides change over the course of a month, why some places have one high tide per day while others have two, and why tides can be gentle in one location and extreme in another. By the end of this lecture, tides should feel less like a background rhythm of the ocean and more like a predictable physical response of Earth's oceans to forces acting on the planet. Tides are caused by gravity, but not in the same sense that the moon pulls the ocean toward it. If gravity acted the same way everywhere on Earth, tides would not exist. What creates tides is the fact that gravity changes with distance. The moon's gravitational pull is stronger on the side of Earth closest to it and weaker on the side farthest away. On the side of Earth facing the moon, ocean water experiences a stronger gravitational pull and is drawn slightly outward. On the opposite side of Earth, the moon's pull is weaker, and the inertia of the Earth-Moon system causes water to bulge outward in the opposite direction. These two bulges are the basic deformation of Earth's ocean surface that produces tides. The key idea here is that tides are caused by differences in gravitational force across Earth, not by the absolute strength of gravity. That distinction will help prevent a lot of confusion later, especially when we talk about why the sun, which has enormous gravity, plays a secondary role in the tides. So, of course, we talked about tides being caused by gravity and that the moon plays that dominant role. So, a natural question follows immediately. If gravity is the key, why doesn't the sun dominate tides? After all, the sun is enormously massive compared to the moon, and its gravitational pull on Earth as a whole is much, much stronger. The answer lies in an idea that is subtle but extremely important. Tides are not caused by how strong gravity is, but how much gravity changes across Earth's diameter. In other words, tides depend on differences in gravitational pull from one side of Earth to the other. Although the sun's gravity is strong, it is very far away. Because of that distance, the sun pulls on the near side and the far side of Earth almost equally. The difference in gravitational force across Earth is therefore relatively small. The moon, on the other hand, is much closer to Earth. Even though its total gravitational pull is weaker, the difference in the pull between the near side and the far side of Earth is much larger. That difference is what produces the tidal bulges. This is a crucial distinction for students to grasp. Tides are not about which object has more gravity overall. They are about which object creates the largest gradient in gravitational force across Earth. Once you understand that, a lot of the misconceptions about tides will disappear. Even though the sun's tidal effect is weaker, it is not negligible. Solar tides interact with lunar tides in predictable ways. Sometimes they reinforce each other, and sometimes they partially cancel each other. That interaction does not change where tides occur, but it does change how large they are over the course of a month. And we will talk about that in a few minutes. But for now, the foundational idea is very simple. The moon dominates tides because it creates the strongest difference in gravitational pull across Earth, not because it has the strongest gravity overall. So at this point, we talked about how tidal bulges form due to uneven gravitational pull from the moon. The next step is understanding why tides occur on a regular daily schedule at coastlines. To do that, we need to think carefully about what is moving and what is not moving. The tidal bulges themselves are not fixed to Earth's surface. They are approximately aligned with the moon, which means their position in space is controlled by the Earth-Moon system, not by any particular location on Earth. Earth, meanwhile, is rotating underneath these bulges once every 24-hour period. That rotation is what causes coastlines to pass into and out of regions of elevated sea level. As a coastline rotates into a tidal bulge, the ocean surface there rises. That is what we call high tide. As the coastline continues rotating and moves away from the bulge, sea level falls, producing low tide. Because these are two bulges, one on the side of the Earth facing the moon and one on the opposite side, many locations experience two high tides and two low tides during each rotation of Earth, or each day. It's important to pause here and emphasize what is not happening. Water is not being pulled directly toward the moon at a particular coastline and then released. Instead, Earth is rotating through a standing pattern of ocean surface deformation. The tide is not chasing the moon across the sky, the land is moving through the tidal pattern. This distinction helps explain why tides are predictable. Earth's rotation rate is stable. The moon's orbit is stable. As a result, the timing of tides follow a regular pattern that can be calculated far into the future. However, the cycle is not exactly 24 hours long. The moon moves slightly along its orbit each day as well, which means Earth must rotate a little more than one full turn to realign with the tidal bulge. That extra rotation adds about 50 minutes to the tidal day. It may be important now to remind you that it takes 27 days for the moon to orbit the Earth. So as the Earth makes that 24-hour rotation, the moon is moving forward along its orbit. This is why high tide occurs later each day rather than at the same clock time. Understanding this timing helps you see tides not as random or local events, but as the result of large-scale predictable motion in the Earth-Moon system. Before moving along to the next slide, it may be worth pausing the video here to take a close look at this illustration. Start from the left side and take note of the moon's position, the tidal bulges, the North Pole, and the location of the little character on the planet. At 0 hour, the character is standing in the center of the bulge, therefore experiencing a high tide. As Earth rotates to the 6-hour mark, you will see the character is now out of the bulge and experiencing low tide. The character has not changed their location on Earth, but Earth's surface has moved along that 24-hour rotation. In other words, if that character was originally standing on a beach in California, that character is still on that same beach 6 hours later. What has changed is the relative positioning of Earth's surface to the moon and to the bulge. Before moving to 12 hours, notice the moon has shifted slightly forward in that 6-hour period. So that bulge has also slightly shifted just a little bit. Pause now for a few minutes to study the rest of this figure before moving forward. Now that we understand why tides occur on a daily cycle, the next question is why different coastlines experience different tidal patterns. If tides are driven by the same gravitational forces everywhere, why doesn't every location have the same number of high and low tides each day? To answer this, we need to shift from thinking globally to thinking locally. While gravitational forcing is essentially the same everywhere on Earth, the ocean does not respond uniformly. The response depends on how water can move in a particular region, and that depends on the physical layout of the ocean. Some coastlines experience semi-diurnal tides, meaning 2 high tides and 2 low tides per day, with roughly equal heights. This is the pattern many people think of as a normal tide, but it's not universal. Other locations experience diurnal tides, with only 1 high tide and 1 low tide each day. You'll notice the east coast of the United States has a semi-diurnal tide, but in the Gulf of Mexico, we see a diurnal tide. And still other locations experience what we refer to as mixed tides, where they have 2 highs and 2 lows, but with noticeably different heights to those tides. These patterns arise because tidal motion is influenced by the way ocean water can move in response to tidal bulges. Factors such as water depth, coastline shape, and the orientation of land masses affect how the tidal signal is expressed locally. In some places, the second tidal bulge is weakened or delayed, leading to a single dominant high tide each day. In others, both bulges are expressed clearly. The key point here is that tidal patterns are not arbitrary. They reflect the interaction between global forcing and local conditions. The moon does not decide whether a coastline gets 1 or 2 tides per day. Instead, the coastline's physical setting determines how the tidal wave is experienced there. This is an important conceptual transition. Students often assume that if a process is global, its effects must be uniform, but that's clearly not the case. Tides are a clear example of why that assumption fails. The forcing is global, but the response is shaped by the environment in which the forcing operates. Recognizing this prepares us for later discussions of tidal streams, tidal currents, and coastal processes, all of which depend on how water movement is constrained and redirected by local geography. So far, we've focused on the daily rhythm of tides, why coastlines experience regular rises and falls in sea level. But if you observe tides over a longer period of time, you notice something else. The height difference between high tide and low tide changes over the course of a month. Some high tides are much higher than others. Some low tides are much lower. These monthly changes are caused by the interaction between the lunar tides and the solar tides. When the moon and sun line up with Earth, their tidal effects reinforce each other. This happens during new moon and full moon phases. When this reinforcement occurs, the difference between high tide and low tide becomes larger. These are called spring tides. The word spring here does not refer to the season. It comes from the idea of the tide springing forth or expanding. Spring tides occur twice each lunar month and represents times of maximum tidal range. Spring tides give us our highest high tides and our lowest low tides. In contrast, during quarter moon phases, the moon and sun are positioned at roughly right angles relative to Earth. In this configuration, the solar tidal bulge partially offsets the lunar tidal bulge. The result is a smaller difference between high and low tide, known as a neap tide. Neap tides give us our lowest high tides and our highest low tides. What's important to emphasize here is that this is not random variation. Spring and neap tides occur on a predictable schedule because the moon's orbit and Earth's orbit around the sun are predictable. Once again, tides demonstrate how large-scale celestial motion translates into regular physical patterns in the ocean. One of the most striking things about tides is how much they vary from place to place. In some locations, the difference between high tide and low tide may be less than a meter. In others, it can exceed 10 meters. These differences often surprise students, especially when they learn that the same moon and sun are acting on the entire planet. To understand this variation, we need to separate tidal forcing from tidal response. The forcing, gravity from the moon and the sun, is global, but the response, once again, depends on how water can move in a particular location. Several factors influence this response. Water depth matters because shallow water restricts how water can move vertically and horizontally. Coastline shape matters because narrowing bays or inlets can funnel water into smaller spaces, increasing tidal height. The size and shape of enclosed or semi-enclosed water bodies also matter, because water can build up more easily in confined regions. This is why extreme tides tend to occur in specific geographic settings, such as long, narrowing bays, like the Bay of Fundy, as an example. These locations do not experience stronger gravity, they simply respond more strongly to the same forcing. Understanding this distinction helps you avoid the misconception that tides are inherently stronger in certain parts of the world for mysterious reasons. That's not the case at all. So up to now, we've mostly described tides in terms of vertical motion, sea level rising and falling. But that vertical change cannot happen without horizontal movement of water. Whenever the tide rises at a location, water must flow into that area. When the tide falls, water must flow out. This horizontal movement produces tidal currents which reverse direction over the tidal cycle. During incoming tide, currents flow toward the coast or into bays and into estuaries. During outgoing tide, that they reverse and flow seaward. In narrow channels, estuaries, and inlets, tidal currents can be extremely strong because large volumes of water are forced through relatively small openings. These currents play a major role in mixing water, redistributing sediments, and transporting nutrients and organisms. This is an important conceptual bridge. Students often think of tides as vertical motion and currents as horizontal motion. But tides involve both. Recognizing this helps you understand later discussions about circulation and coastal processes. So far, we've talked about tides as predictable, repeating motions of the ocean surface. But tides are not just abstract cycles. They have very real consequences at the coast, especially when tides reach their extreme values. To understand why tidal extremes matter, we need to think carefully about what happens when the ocean reaches unusually high or unusually low water levels. During very high tides, the ocean reaches farther inland than it normally does. This increases the area exposed to wave action and allows waves to interact with parts of the coastline that are usually dry. Over time, this contributes to erosion, sediment redistribution, and changes in shoreline shape. When high tides coincide with storms or strong winds, the effects are amplified. Waves ride on top of already elevated sea levels, increasing the risk of coastal flooding. When Hurricane Idala made landfall over Horseshoe Beach in Florida on August 30th, 2023, it was only a Category 3 storm. But it hit right after a full moon during an incoming tide event. So the timing of this storm created a 15-foot storm surge that flooded thousands of homes. The timing of the storm associated with spring tide created a situation where water was pushing over other water. But the location was also a factor. The storm landed in the area some people refer to as the armpit of Florida. The shape of the coastline here forms a bit of a funnel effect where the water is pushed into the corner, and that is exactly where the storm hit. At the other extreme, very low tides expose large areas of the sea floor that are normally underwater. In rocky and sandy intertidal zones, this exposure affects temperature, moisture availability, and oxygen levels. Organisms living in these environments are adapted to regular exposure, but extreme low tides can push those adaptations to their limits, especially during hot or cold weather. It's important to emphasize that these extremes are not random events. They occur as part of a predictable tidal cycle, particularly during spring tides. This predictability allows coastal communities, scientists, and managers to anticipate when extreme conditions are likely to occur. From an oceanography perspective, Tidal streams illustrate how relatively slow, regular motions can still have powerful cumulative effects. Tides don't need to be violent to shape coastlines and ecosystems. Their influence comes from repetition, timing, and interaction with other physical processes. So maybe it's worth taking a step back and asking why oceanographers devote so much attention to tides in the first place. After all, tides don't transport water across ocean basins the way currents do, and they don't generate dramatic surface motion like waves. So why are they important? The answer lies in the amount of water and energy involved. Even though tidal motion is relatively slow, it involves the movement of enormous volumes of water. As tides rise and fall, water is constantly being redistributed along the coastlines, across continental shelves, and through estuaries. This redistribution enhances mixing between different water masses. Mixing is one of the most important physical processes in the ocean. It influences temperature distribution, nutrient availability, oxygen levels, and biological productivity. In many coastal and shelf environments, tidal mixing is the dominant mechanism that keeps water from becoming strongly layered or stagnant. Tides also interact with other forms of ocean motion. Tidal currents can strengthen or weaken wind-driven currents, can influence sediment transport, and can modify how waves behave near shore. In shallow environments, tides often set the background conditions that determine whether other processes can operate effectively. For marine organisms, tides structure daily and seasonal rhythms. Feeding, reproduction, and movement patterns are often synchronized with tidal cycles. From an ecosystem perspective, tides are not just physical drivers. They are part of the environmental context in which life operates. Understanding tides, therefore, is not optional background knowledge in oceanography. It is a foundational piece that connects physical processes to biological and ecological outcomes. As we near the end of this lecture, it's important to place tides within the broader framework of ocean motion. Throughout the course, we've been building a vocabulary for different ways the ocean moves. Tides are one of those ways, but they are not the only one, and they are not interchangeable with others. Tides are an example of oscillatory motion. Water moves back and forth around a position, rising and falling, or flowing in and out, but there is no long-term net transport of water in a single direction. This distinguishes tides from surface currents, which we will examine next, where water is persistently moved from one region to another. At the same time, tides are fundamentally different from wind waves. Wind waves involve motion primarily at the surface and operate on short timescales. Tides involve the entire water column and operate on daily to monthly timescales. With tides now clearly defined and understood, we are ready to move forward to examine surface currents, where sustained wind forcing produces net transport and large-scale circulation patterns. Throughout this unit, we have been distinguishing between different ways the ocean moves. Wind waves moves energy across the surface without transporting water long distances, Tsunamis are long wavelength gravity waves that involve the entire water column but still represent oscillatory motion. Tides, as we have now seen, are also oscillatory. They involve the rise and fall of sea level and the back and forth movement of water. But over time, water does not steadily move in one direction across the ocean because of tides alone. That idea, oscillation versus transport, is going to matter enormously in the next lecture. Surface currents are fundamentally different from tides. Instead of water moving back and forth around a position, surface currents represent net transport. Wind pushes on the ocean surface persistently in one direction. That force, acting over time and modified by Earth's rotation, produces circulation patterns that move water masses across entire ocean basins. Next lecture, we will learn about currents.